pleased to introduce Dr. Zygmunt Pizlo. Dr. Pizlo is a professor of mathematical and computational cognitive science at Purdue University. His research focus is on the cognitive processes involved in perception, navigation, problem solving, and developing computational models of these mechanisms. Today he will present a talk titled Symmetry provides a Turing-Type test for 3D vision. Please silence your devices, but don't put them away. We want to see you tweeting to the hashtag Dawn or Doom. Please join me in welcoming Dr. Pizlo.
Thank you. So, the context of this conference suggests to us to ask some questions like whether robots will be smarter than we are, whether they will be smarter soon or ever, and can robots even hope to be smarter than we are? If we want to answer this question, we must first find a way to determine whether robots actually have minds, and if they do, what's in them. I would like to point out that a robot cannot produce what looks like smart behaviors if it has no mind. Having mind, in my view, means at the very least that one keeps and uses a representation of the external environment and events. I don't have time to explain why I think so, but this is one of my assumptions. So, can robots be intelligent? This is one of the oldest questions in artificial intelligence, which started like 60 years ago. And Alan Turing, you may remember the recent movie about Alan Turing, proposed a test to determine whether computers can think, and the idea was that I let you talk through email to someone else, and you either talk to another person or you talk to a computer, and if you cannot tell the difference which is which, then we could conclude that the computer is like a person, that the computer is intelligent. This is a simple version of what he described, but this test has been taken quite seriously. How good is this test? In 1980, a number of people were criticizing this test, but one of the perhaps most influential was Searle's criticism. He used what he called Chinese room argument, which goes like this. Assume that you are in the room, you don't know any Chinese, but you know English. You have some English rules for manipulating Chinese symbols, and someone brings text written in Chinese to the room, then you use your rules of translation or rules of how you actually manipulate symbols, and then you return the response. And for Chinese person outside, they may have an impression that you actually understand Chinese when in fact you don't. So the point of Searle's argument was just that by observing behavior, it's actually impossible to decide what's in the person's mind, and in particular whether the person understands, whether the person is intelligent. Searle actually went even further when he said that this test is not just the limitation of how the test was designed. In his view, computers will never be able to think because only biological beings will be able to think. He said that computers are made of transistors, which are physical, not neurons, which are biological. So it is pointless to even try to produce artificial intelligence, where by artificial intelligence you mean a computer which is as smart as we are. So these are two claims by Searle, and I will return to the second claim about how important is the physical stuff as opposed to biological. But first I want to examine how difficult or how easy is to say something about what's in somebody's mind by observing his behavior. So one of the classical examples is like this. We have tests in experimental psychology where I can verify how well you can discriminate, how well you can tell apart different colors. And I can, for example, determine whether one person can tell colors apart better than another person. We know how to do it. However, no one, as of today, and quite possibly never, will be able to determine whether your percept when you look at the green is the same as my percept when I look at green, as opposed to perhaps my percept when I look at red. We both use the same word, green, because we learned how to associate the word green with the given patch, but we actually don't know what your percept is when you look at red and green. And no one, as of today, is actually even hoping that we will ever have a test that will be able to verify this. It is hard to detect if someone is telling the truth or not. So here are two paintings. They are painted by different artists. And if I tell you that I like one better than the other, you actually don't know whether I told you the truth or not. And it's not clear how you would verify this. I mean, you could ask me how much money I would spend, but this may or may not be related to how much what's the aesthetic value of the painting for me. Take another problem. I give a student a geometry problem, say construct a triangle given its perimeter, angle at one vertex, and the length of altitude drawn from this vertex. The student does nothing for a while. Is she thinking about this problem or about the failing grade that she's going to get? By the way, this is not an easy problem. So you could think about your favorite AI system like Deep Blue or Watson, and it's not clear that those systems could even begin solving this problem. So now let's consider an example where it is not only possible, but actually easy to uncover the state of somebody's mind. Are you ready? So anyone looking at an animal like this tiger would say that he sees a symmetrical animal. In this case, mirror symmetrical. The left half and the right half of the body are identical. And we can actually be quite sure that when you look at this picture that you have in your mind a symmetrical representation of the object. We know that you perceive symmetry because the same way we could verify how well you can tell colors apart, we can now verify how well you can tell one half of the subject from another half of the, one half of the object from another half of the object. Sometimes I can make the halves identical, on some other case not identical, and we know how to verify this. So suddenly we actually can verify whether symmetry is in the observer's mind when the observer is presented a symmetrical object. So I'm going to try to convince you that symmetry connects physical, biological, and mental events. The cat is actually symmetrical, so symmetry exists both in biological world, animal body, and in the mental world, the observer's percept. So if we want to extend this argument to robots, which are made of physical stuff, we must show that symmetry exists in the physical world as well. And now you can remember Searle's argument that robots will never be intelligent, never be like us, because the robot, the CPU computer, is made of transistors, not neurons. And it actually, we've known for a long time that physical world is almost all about symmetry. If you take atoms and compounds, like if you take a carbon atom, which actually is a basis of organic chemistry, when it starts forming compounds, the geometrical configurations are symmetrical. In this case, you have two perfect regular tetrahedra. And in fact, carbon, because of its symmetry, can form long chains of compounds, which are essence of life. All planets and stars are symmetrical. They are spheres, they are spherical. And spherical means symmetrical because when you rotate the sphere, you obtain the same sphere. So what I'm now saying is that there is more than one type of symmetry. The cat's body is mirror symmetrical, but the planet is spherically symmetrical. All crystals are characterized by symmetry. So in fact, this is really the best way to classify crystals and analyze their properties is by evaluating their symmetries. If you take the special type of crystals, ice crystals called snowflakes, they have plenty of symmetries. And the symmetries are not accidental. They are always look like regular hexagons. The forces in physics are symmetrical. So gravity is symmetrical. Since the Earth is spherical, the forces have the same type of symmetry. Electrical fields are symmetric as well. If you have a point charged, you have a spherical symmetry. If you have two planes, you have a different type of symmetry. Obviously, all plants are symmetrical. They're not necessarily perfectly symmetrical, but they have a great deal of symmetry. Animals, like this butterfly, is mirror symmetrical. In fact, all animals, perhaps except one, are almost perfectly mirror symmetrical. Your brain is symmetrical. You have two hemispheres, and they are similar to each other. And your DNA is symmetrical too, right? There are those two very regular parts of the DNA. So symmetry is everywhere we look. For the record, the concept of symmetry that I used so far is actually more general than what I indicated, but for the purpose of this talk, what we covered so far would be sufficient. So symmetry actually provides like building blocks for physical, biological, and mental phenomena. And symmetry, you cannot really say, symmetry doesn't really belong exclusively to any of those three worlds, physical, biological, or mental. Symmetry can actually be considered what Spinoza, Fechner, and others would call neutral stuff in their theories of mind-body. And whether we observe physical, biological, or mental symmetry simply depends on observation tools that you use. If you look at something and you see symmetrical objects and you think about what you see, this would be a psychological observation, or if you describe the body, or if you analyze the compounds of the individual cells. Pretty much everyone up to this point in this discussion of mind-body problem, in the discussion of AI, ignored the concept of symmetry, including Searle. And even though transistors are different physically than neurons, symmetry actually exists in both. We just showed that symmetry exists in physics pretty much everywhere. And it is symmetry which makes it possible to compare the computer CPU and human mind in a meaningful way. And the rest of the talk will essentially elaborate on this observation. One could argue that symmetry is essential for both. All other features are probably superficial. But there is more. So if you look, there is quite a big literature on symmetry. Symmetry in physics, in mathematics, in biology. We are getting more and more papers about symmetry in perception, in human perception. But there is more to it than just symmetry. Physics is based on three fundamental principles. One is symmetry or invariance, and this is what I just briefly discussed. The second one is the least action principle, and the third one are conservation laws. And in the rest of the talk, I'm going to show you that we can identify all those three principles in perception and cognition. In fact, I would argue that you really have to use those three principles if you want to do a good job. So we discussed symmetry a little bit. Now I will go to conservation laws, and then I will get to the least action principle. We'll see what we get at the end. So in physics, there are many conservation principles. There is conservation of energy, momentum, angular momentum. I will illustrate only two because of simplicity. So let's first watch this YouTube. And so here's the guy in the space station. So there is zero gravity. Zero gravity is not essential for the demonstration of the conservation of momentum, but perhaps it makes it easier. So he has two tennis balls which have equal masses, and he produces a collision between those two balls. What is important for us is to realize that the balls move in some way, like with some velocities before the collision, and after the collision, they change the directions and the speeds. So there are several aspects that change before and after the collision. But if you compute the momentum, which is the product of the mass and velocity, the total momentum is the same before and after. In this case, one of the ways he's trying to illustrate is that if one ball is stationary and the other is moving, after the collision, the moving one stops and the second one moves. But this is just a special case. Here he put two pieces of Velcro to show that when they glue to each other, the velocity changed, but now they move together. Still, the momentum is conserved. At the end, he will try 4 times to produce a bump so that they get glued. It takes him 3 times to figure out how to do it, right? So they end up being glued. What it means is, in this case, the velocity of the 2 balls afterwards would be half of the velocity of the individual of the first ball. So collision is a transformation. Many things change, but not everything. And momentum is preserved. We call it conserved. The second example, perhaps even more fun, here you have this skater which performs pirouette. And when she's changing the position of hands and legs, the angular speed is changing. So the angular speed is changing, the geometry of the person is changing. But if you compute the angular momentum, if you know how the formula looks like, the angular momentum stays the same. So there are many examples like this in physics. And it doesn't mean that everything gets conserved. So you have to be very careful. Something gets conserved, others don't. So how about conservation in 3-dimensional perception? Consider this case. So I take a 3-dimensional object. This screen could represent a computer screen. It could represent the image in your iPhone, or it could represent an image on the back of your eye. The important thing is that in visual perception, the 3-dimensional object is being transformed into 2-dimensional image, and then the brain produces 3-dimensional percept, which is identical to the original object. Not everything is the same, because we cannot claim that the weight of your percept is the same as the weight of the object. But we actually can claim that the shape that you perceive, the shape in your mind, is identical to the shape of this object. So there is a transformation from physical world to your mind, and the shape goes through those two type transformations. The second one, when your brain is producing 3D percept from 2D image, is actually an inference. So the visual system is performing inference. This way the observer knows what's out there. And if the perceived 3D shape is identical to the geometrical shape of an object, we can talk about conservation of shape. It is sometimes called veridicality of shape perception, but in this context, I want to use the term borrowed from physics, because I can use the principles, the mathematical principles that physicists use to actually explain the percept. So now, we know that humans can see 3-dimensional objects and perform this inference. The question is, can the robot infer anything interesting, and whether it can infer anything which is human-like? Now we will need the third principle in physics, which is called least action principle. And so up to this point, I started with symmetry, showing you symmetry of animals and symmetry of atoms. Then I briefly discussed conservation laws in physics, and I argued that corresponding conservation may exist in vision. Now I will show you I will show you a couple of examples of least action principle in perception first, and then I will show you the corresponding principles in physics. In perception, it is called simplicity principle. In philosophy of science, it is called Occam's razor. In information theory, it is called minimum description length principle. The idea is that the observer takes the data and asks what's the simplest interpretation of the data. Let's take this example. All right, so here is a picture of a chair, and when I rotate it, it's kind of nothing surprising. You see a chair. But now I could, by keeping the image, I could change the depth of individual points. So I'm actually now messing the parts in 3 dimensions. I can show you how it looks, right? But I'm only changing the depth of those parts. And by changing the depth, I'm not changing the image. The point here is that I could produce infinitely many of those configurations in 3 dimensions, and they all look like mess. Only one of those is symmetrical in 3 dimensions. So when I give you the image like this, and you see 3-dimensional object which looks like a chair, it is not because you've seen many chairs in your life. It's because the 3-dimensional object which has geometry of a chair is the simplest, the most symmetrical interpretation of this 2-dimensional image. Right? There will be a couple of more examples in a second. And simplicity principle leads most of the time to accurate percepts, which, as we pointed out, are conservations. So let me show you now a few other examples. So let's take it in steps. So look at this image. It is an image of a Jeep. And when you look at it, you see 3-dimensional object, which probably is not very different from what I'm showing you here. This is actually a 3-dimensional model that was used to produce this picture. So if by looking at this image, you see a 3-dimensional object like this, your percept is veridical, or we could say that we are dealing with conservation of shape when we go from the physical object to your percept. Here we drew some of the contours from the Jeep, and we applied our simplicity principle. So in other words, we have an algorithm. So we have a camera which is looking at things, and then it's running some algorithm with simplicity principle, and our robot can produces this interpretation, which is pretty much identical to the overall shape of this object. So you could say in this case 2 things, that you perceive the object accurately and the robot perceives the object accurately, and the 2 percepts are identical. So this is an example of what I say a good Turing test, because now I know what's in your mind because I know how your visual system works, and since I wrote an algorithm for the robot, I know what's in the robot's mind. I can show you maybe one or 2 other examples. This doesn't have to be a Jeep, it could be a bird. It's the same idea. This reconstruction here is produced by our robot when looking at this line drawing. And this is the original 3D model. And you can ask yourself, what do you see when you look at this single image? Let's see whether I want to show anything else. Here, it's actually, we found a praying mantis behind the psychology building. So this is the actual photo. When you look at it, you see a mantis. And we drew by hand some of the contours of the mantis. Our robot applied its algorithms using simplicity principle, and this is the robot's perception of the mantis. I bet that it is not very different from yours. All right. So you see shapes veridically, and the robot can see them as well. In both cases, veridicality is produced by the least action principle called simplicity. And simplicity principle works not only for 3-dimensional shapes, it works for 3-dimensional scenes and for most of the 3-dimensional world. So now I owe you at least a couple of examples about simplicity principle or the least action principle in physics. It's really everywhere, but I will show you only 2 examples, in optics and in electricity. In optics, I will choose the example of light refraction. So if the light is traveling from one medium to another, let's assume that this is an air and this is a glass or water, the speed of light is different in the 2 media. So the light will get refracted, it will be bent. And there is a rule for how the bending proceeds. It's the ratio of sines of the angles is equal to the ratios of the speeds of light in the 2 media. But interestingly enough, Fermat way of explaining this phenomenon, light refraction, is to point out that when the light starts here and ends there, assuming that this is like a collimated beam of light or a single ray of light, the light actually, even though the light could choose infinitely many trajectories. It could actually go all over the place and come here. It could actually perhaps go along the straight line, but it doesn't. It goes along this line, which is not a straight line, because this trajectory minimizes the total time of travel. And no matter how complex the optical medium is, Fermat principle works. The light minimizes the time of travel. There are a couple of examples where I can show that light maximizes time of travel, but in both cases it is an extremum principle. Most of the time physicists talk about least action principle, but you should be careful that it is more general than that. Another example is the Kirchhoff's laws for circuits. This is, in fact, an example of one of those interesting tests in electrical circuits. So we form a cube from resistors. Let's assume that all resistors are identical, but they wouldn't have to be. Let's assume that we apply some voltage between A and B, and then the current will distribute itself in those branches. Now, if the resistors are identical, it will distribute itself in some quite regular way. But if the resistors are not identical, it will distribute itself some other way. One way to solve this problem is to apply Kirchhoff's laws for currents and voltages. But what essentially Kirchhoff's laws are saying is that the current, when going from A to B, will distribute itself in such a way so as to minimize the total amount of heat generated in the system. How does the current actually know this? It's an interesting question, and there are some answers how it goes. But it so happens that most of the physics, if not all, can actually be explained, or at least events can be explained by using least action principles. So now we have all three principles, and what is interesting is that the least action principle is the link in physics between symmetries of natural world and conservation laws. And this has not been demonstrated until 1918 by German mathematician Nother. It's called Nother's theorem. And it turns out that for every symmetry of a natural phenomenon, there is a corresponding conservation law. And there is one-to-one mapping, which is established by the least action principle. And I can just briefly mention two examples. So, conservation of energy can be produced or derived by applying least action principle from symmetry in time dimension. How do you do symmetry in time dimension? Let's assume the following scenario. Let's assume that we set up some experiments in this room. I take an object and I will drop it, and we measure the time, acceleration, and we know that the movement of bodies under the gravity is according to Newton's laws, so we know what's going to happen. There is some noise in the measurements, but approximately we know what's going to happen. If we perform the same experiment in this room tomorrow, we expect the same outcome. What this means is that moving our experiment along the time axis does not affect the natural phenomena. When you apply corresponding least action principle to this symmetry, you derive conservation of energy in physics for closed systems. Similarly, if you take space symmetry, so we perform our experiment in this room and we perform it in the next door, we expect the same outcome because the natural phenomena don't depend on the translation in space. If you apply the corresponding least action principle, you derive the conservation of momentum, which are illustrated in the beginning. So, three-dimensional vision is almost like our first summary. So, simplicity principle in visual perception is applied to images of symmetrical objects, and this results in accurate perception of three-dimensional shapes, which is conservation of shape. And this is analogous to physics when least action principle is applied to symmetry of a phenomenon resulting in a corresponding conservation law. Can this approach be extended beyond three-dimensional vision? I would say that almost certainly should. If we take examples like language problem solving, data mining, the issue is there is always enough structure and regularity in the problem that you are thinking about that you can define symmetries or invariances in the particular domain. And again, you have to use the mathematical definition of symmetry to do it. But whenever there is a regularity in something, you can define symmetry. Then you have to figure out some good least action principle which allow you to infer something important or interesting from the symmetries that are present. So this will lead to conservations that provide key to understanding pretty much our environment and for understanding each other, really. So what I'm saying is that those tools, symmetries, the least action or simplicity principle and conservation laws are the proper tools to actually talk about cognitive phenomena in psychology. This is the good way to describe, uncover, explain somebody else's mind. And in this case, you could actually explain the robot's mind as well, because there is no reason why you shouldn't be able to do it. So Nother in 1980 showed that without least action principle, there would be no conservations in physics. Weiner in 1960, he pointed out that without symmetries in nature, there would be no loss of nature. What I'm suggesting here is that without all three elements, symmetry, least action, and conservation, there would be no human mind as we know it and no intelligence. In other words, we wouldn't be able to understand the physical environment or each other. What does this mean for the intelligence of robots? If a robot does not use these principles, it cannot be smart. If the robot uses these principles, we should be able to understand the robot. Our natural sciences, at least as of today, do not offer any magical fourth principle that would allow robots to be smarter than we are. So, if singularity, if it is defined as super intelligent robots, namely robots that are too smart for us to comprehend them, is not likely to happen. And if it does happen, it is not likely to be an elaboration of currently existing AI systems. Thank you very much. Questions, comments, criticism?
One of the first intelligent decisions I've heard about robotic intelligence.
Thank you. Any other criticism along these lines?
Well, it's not really criticism. It's just that I feel that as methods for robots evolve, I feel like it's just that we're just keep adding features of what we mean by intelligence.
Mm-hmm. Yeah.
Hello?
Yeah, it works.
So I was wondering is there enough features so we consider intelligence, or we just keep increasing the threshold so robots will never be considered intelligent for us?
Yeah, so there are like two aspects in it. It's true that over time, like during the last 100 years, the definition or the criterion for what it means to be intelligent is shifting. So some time ago, playing chess is considered to be intelligent, or reading a text or something, right? So, or recognizing even letters in the printed text, or multiplying numbers. So as we develop AI, then whatever AI can explain, we say this is not really an intelligence. Intelligence is everything else. So this is a good point, and I think there is nothing wrong with this, because this way you kind of provide stimulation to both communities. Psychologists who are working on human mind will try to keep demonstrating how smart human mind is, so that the colleagues in electrical engineering department cannot replicate it. The EE or CS people will try to push the envelope so that the boundaries get shifted, right? But at the end, the question is where we are at this point, and whether there is still something in human intelligence that we are not aware of, whether those three principles actually are sufficient. In my mind, and this, the last slide is kind of, the last line on this slide is suggesting is that the development of AI during the last 20 years, I think it's kind of was going in the wrong direction. So you have a program which can play chess, but the program doesn't really know who is playing with. Or if you ask the program to play Jeopardy, it probably wouldn't be able to do it. So there was this big push to develop algorithms to solve some specific aspects without asking whether the machine system has any mind. And this is what I said in the beginning, that just by demonstrating smart behavior doesn't imply that it is intelligent. And one way to view it is that the chess-playing machine, as of today, cannot solve a geometry problem or vice versa.
You started out your talk with the two pictures and saying that I could not detect a lie, that you
Right.
were lying. Are you familiar with the current, some recent research that was released about the use of MRI and its indication of evidence of a lie?
Yeah, so there are those methods existed for a while. The assumption is that if you are lying, you get nervous, you sweat, or something in your brain is changing. But as of today, we don't have a theory of the brain. So when we do MRI and we try to detect a lie in the MRI picture, we could establish some statistical relation, but we don't know why this relation is happening. And as of today or yesterday, this relation was far from perfect. So no one would really, if I'm giving a class course in graduate school and I give an exam, there's no way that I could say, okay, I'm not giving an exam because I know what's in your mind, or I can ask you questions and I know whether whether you are solving the problem the right way or the wrong way. So those methods will keep developing using statistical learning, but they are very far from being perfect. So in this sense, they do establish some relation, but it is only statistical relation. So therefore, in a particular case, like with this painting, you could say with probability 60%, you say that I'm lying. But there's no way that the court system, judicial system could start using those tests and ask person, did you actually kill the other guy? And based on the answer, there would be a decision. So we are very far from it.
The algorithm that was used in your presentation for looking at the symmetry of the chairs and other objects like that, that algorithm was specifically for interpreting three-dimensional shapes. How would you be able to, or do you think you would be able to create an algorithm that would look at symmetry in a more broad sense of the term, as kind of our brains are able to perceive that?
Yeah, so this, I did mention on one of the slides the principle which is called minimum description length principle. So experts in information theory and computer science are claiming that we are getting better and better understanding of some universal definition of what simplicity of a signal is. So it could be shape, it could be piece of music, it could be sentence, spoken sentence or written sentence. It so happens that nature is simpler than the data that we acquire from nature. And the claim is, and there is very good support for the claim, that when you get the data, and if you ask what's the simplest interpretation of the data, now it is not easy because there are always infinitely many possible interpretations, but if you narrow down the interpretations, the claim is, and there is evidence, that you are likely to get the correct interpretation. So symmetry is one big element of simplicity. Perhaps symmetry can be generalized so that, in fact, it is much broader than what I mentioned. When I teach about symmetry, I tell students that one definition of symmetry is that it is self-similarity of an object or event. So if one part of something is similar, not necessarily identical to some other part, then we can talk about symmetry. But what this means is that pretty much any type of structural redundancy in object, in signal, in whatever you have, could be handled by tools of symmetry. So, and typically when we have a signal or object or any kind of data, we have a part which is completely random part, and we have part which is redundant. And the claim is that the redundancies in signals can be called symmetries. So the work is not finished, but there are several groups around the world which are actually going in this direction.
So in industry, they're trying to not go to first principles, but they're attacking problems like image recognition and natural language processing with neural networks, with things like word-to-vec and phrase-to-vec and deep face and that kind of thing. So their attack is very difficult to get understanding from it. You can get an answer, but the efforts in doing the reverse of those things, they've showed some images recently that sort of look like insanity. And so do you have any comments on that particular effort? And if you criticize it, then how can these attacks be brought forward to compete?
Yeah, so one should be careful with very strong versions of this criticism. So the common approach in industry or in engineering when solving problems from at least massive amount of data is to apply the machine learning methods to lots of data and try to learn some regularities from it. So this is essentially trying to infer empirically some regularities in the data instead of using first principles like the concept of symmetry. It's trying to figure out from the massive amount of data that symmetry was probably there and it was important. So if you had enough time with this learning, and I don't know what enough means, it could be a week, maybe it could be 100 years, in principle you should be able to, by using empirical methods, to produce results which would be identical to the methods which are based on those abstract first principles like symmetry. Whether this is going to happen or not, it just depends on how complex the world is. So in the case, we did play with this several years ago, and we put some data in the paper that we published. So we showed to an algorithm a picture of a symmetrical object. But the picture of a symmetrical object itself is not symmetrical, because you can look at the object from different viewing directions. And the question is, how long would it take for an algorithm to be able to decide whether the picture is a picture of a symmetrical or asymmetrical object when none of the pictures were symmetrical to begin with? And this is very difficult for this brute force approach. On the other hand, if I tell you, look, I'm going to show you two-dimensional pictures of 3D objects, some of them symmetrical, some of them not, now the task for you is trivial. So my claim would be that often, maybe not always, but often using good, smart, abstract criteria, principles, priors, is much more effective than trying to learn them by brute force from the data.
Okay, so as far as I understand it, this slide says that because we're limited to 3 fundamental laws of physics, that super intelligent robots are highly unlikely.
Right.
But you've already said previously that these laws apply, throughout biology, in the physical world, blah, blah, blah. So that means even for animals, these things probably apply. And we already know that there are intelligence differences between us and, let's say, chipmunks.
Right.
So from the chipmunks' perspective, we are too smart for them to comprehend us.
Right.
So why is it so unlikely that we're the top? And what makes us the hard limit? That nothing can be smarter than us, but we can be smarter than lots of stuff.
Right. Yeah, that's a good point. This is why I'm not really making absolutely strong claim here. In the case of chipmunks and us, this was a process of evolution. In other words, chipmunks didn't manufacture us. Here we are dealing with a situation that we build some robots, And the concern is that at some point this will get out of our hands, that the robots will be much more intelligent. So I don't know how close this comparison is. In other words, if you let chipmunks to start manufacture robots, how quickly they would produce human beings. Now, this is a question. This is a question of the evolution, and we have some ideas about the natural selection, but we don't really have no one has a computational model of how the evolution went from chipmunks to human beings. So there was something happening during evolution that the humans, which are more intelligent than chipmunks, you could, so what are the things that we have and chipmunks don't have? We have abstract thinking, right? And we have language. Chipmunks, rats, monkeys can solve some problems, but they don't talk too much, and they don't have abstract thinking. So the animals have visual perception. Most of them have visual perception, auditory perception. So they have several types of perception, but they were lacking intelligence and abstract thinking. So this is the two things that were added to produce intelligent humans. And the question is there something else outside of communication, outside of abstract thinking, that could make us even smarter? And it is hard to think what this would be. So what I am saying is not likely to happen. But I am all open. If super intelligence is produced, I want to be the first to have one. The issue is here is, rather than making strong claims about what's possible or not, I'm trying to make a claim that the current work on those machine learning methods, they are probably not going in the right direction. But it doesn't mean that other directions are not possible.
Well, so based on the notion that everything we learn is based on our perception or sensors, in principle, if we build something that's able to learn from its sensors and we build into it much better sensors than we have, then in principle it could be smarter than us.
Be careful. There is evidence suggesting that the old man Plato was right, namely that when you are born, your mind is not tabula rasa. So there are some concepts that are present in the mind of a human or animal, such as symmetry. We know that when the animal or human is born, the mind of the animal knows about symmetry. It doesn't learn from examples.
But you could build that in.
You can build it in. Now, one could push this one step further and say, well, but evolution was pretty much nothing but learning. So it had to be, but we don't know whether the symmetry was actually inferred from the data or whether it was lucky fluke in the mutation that symmetry appeared in the DNA and in the brain. As far as all animals that existed on Earth was always mirror symmetrical. So if you look for a mate, you better know how symmetry looks like, because otherwise you're not going to have children.
Yeah, but back to the notion of sensors versus intelligence, I guess the only difference I could admit to is we have all sorts of quirks, and the behavioral economists are beginning to learn all about those. And if you consider intelligence, human intelligence, then whatever we would make would have to have the same kind of frailties, right?
Yeah. So again, going back to previous example, but maybe making one additional step. So let's assume that you are a newborn animal or human being, and now I keep showing you two-dimensional images of objects. Now the objects are symmetrical, but the images are never symmetrical. So I'm giving you as data hundreds and thousands of two-dimensional asymmetrical images. How long would it take for you to make a lucky guess that the world outside is three-dimensional and full of symmetrical objects?
Yeah, but if I were a robot with a sense of touch, I could manipulate it.
You could manipulate it. This is one way to do it. Yeah. So this is So not everyone is giving up on extracting information from data. There's a big push, and we will see how far it can go.
This corresponds, in some sense, to a lot of the new research in newborns. We used to have the idea that children were basically blank slates that were filled up with information, and new cognitive research shows that's not the case at all. Children are, in fact, child comes out recognizing its mother's voice immediately, because perhaps through exposure to it in the womb, but they have all kinds of cognitive abilities that they're learning.
Yeah, if you are interested in this, there are classes in our department where there is a review of those studies. There is a lot of studies on newborn animals with the perceptual and cognitive abilities. There are fewer studies on human newborn infants because it's harder to do experiments. But there are experiments with infants who are like 1 hour old, demonstrating how much they can see and how much they can understand. There's a question there.
If there was an algorithm that was created that would be capable of something like abstract thought, much like humans are and no really other animals are able to do, then with increases in processing power and other abilities from that, why would that be unable to surpass anything that, let's say, humans would be able to create?
Yeah, it's a good point. So I think that the people who talk about singularity is not an issue that the robots will be like 5 times smarter than we are or faster. The issue is that they would be smarter in ways that we wouldn't be able to comprehend. Now, what is interesting is that the neurons in human brain are devices which are relatively slow. They perform 10 or 100 operations per second. Transistors in your laptop can perform 10 to power 9 or 10 to power 10 processors. Still, there is no computer vision system which can actually do a number of things. I mean, there are systems which can drive a car, although in every Google car there is a person sitting and watching what the computer is doing. So we are getting to the point where the speed of transistors is high enough to compensate for the massive size and complexity of the human brain. Human brain has 10 to power 11 neurons, and each neuron has 1,000 or 10,000 connections. Computers don't have this complexity. So brain is parallel but slow. Computers are fast but not parallel. But as of today, we are almost compensating the complexity by speed. So with the next 5, 10, 15 years, we could actually be seeing some interesting developments where already the Deep Blue, which is playing chess, although we don't even know how many dozen of programmers were actually fine-tuning the chess-playing algorithm, but still the speed of processing can actually compensate for the lack of intelligence. So now the question is what you are asking. So let's add the intelligence and see what happens when we put the speed on top of this. So, but this would not be trivial, because we would have to have a good grasp on what intelligence is. Perhaps this approach is a good way to handle it, but we are just beginning to work on it.
In a previous session, there was a discussion of self-awareness in computers, and I've never heard a good explication or a model of what self-awareness would mean in a computer. Have you considered this, or have you had any thought about this?
Yeah, I read about this every once in a while, but I haven't seen satisfactory criterion or a treatment.
Nor have I.
So there is obviously discussion. It's good that people discuss it, but it looks that at this point it is more a philosophical discussion than scientific discussion. I'm not aware of solid experiments which can get handle on this. Doesn't mean that it is impossible, On the other hand, this question gives me an excuse to make another comment. 100, 200 years ago, psychologists were not sure whether we could do science in psychology to begin with, either with perception or thinking or learning. In other words, when you were a psychologist 150 years ago and you were writing a paper, you really had to convince the audience that you are a scientist rather than a philosopher, because it was not obvious that anything in psychology can be handled scientifically. Today, it's exactly the other way around. The assumption is that all aspects of human mind can be studied scientifically, and there is no reason to believe that that's true. What's more likely is that some things can be studied scientifically, like visual perception, maybe problem solving, and others may not. I gave you an example with figuring out what your percept is when you look at red. And there's no experiment which can decide this. So there are mental phenomena which probably will never be part of science, simply because the system is too complex, is a black box system. We can only observe the behavior in response to the input, and there will be limit in how far we can understand it. And maybe consciousness is one of those which will be difficult to handle scientifically. So I don't work on it. I will start working on it when I know how to run good experiments.
Good answer.
So we are almost out of time. Thank you very much.